Okay, this is section 15.4, electric field lines. Let's get the PowerPoint, and here we go. To help visualize the electric field, we can draw lines pointing in the direction of the electric field vector at any point. These lines, which are introduced by Michael Faraday, are called electric field lines, and they are related to the electric field in any region of space in two ways. Number one, the electric field vector E is tangent to the electric field lines at each point. Number two, the number of lines per unit area through a surface perpendicular to the lines is proportional to the strength of the electric field in a given region. Note that E is large when the field lines are close together and small when the lines are far apart. The figure on the left shows some representative electric field lines for a single positive point charge. Note that this is a two-dimensional drawing, and so contains only the field lines that lie in the plane containing the point charge. The lines are actually directed radially outward from the charge in all directions. Think of the quills on an angry porcupine. Because a positive test charge placed in this field would be repelled by the charge Q, the lines are directed radially away from the positive charge. The electric field lines for a single negative point charge, shown in the figure on the right, are directed toward the charge because the positive test charge is attracted by a negative charge. In either case, the lines are radial and extend all the way to infinity. Note that the lines are close together as they get near the charge, indicating that the strength of the field is increasing. Okay. Drawing field lines. Here are the rules for drawing electric field lines for any charge distribution. The lines for a group of point charges must begin on positive charges and end on negative charges. In the case of an excess charge, some lines will begin or end infinitely far away. The number of lines leaving a positive charge or ending on a negative charge is proportional to the magnitude of the charge. No two field lines can cross each other. The figure shows the symmetric electric field. The figure shows the symmetric electric field lines for 2 point charges of equal magnitude but opposite sign. This charge configuration is called an electric dipole. Note that the number of lines that begin at the positive charge must equal the number that terminate at the negative charge. At points very close to either charge, the lines are nearly radial. The high density of lines between the charges tells us that this is a strong electric field. There is a strong electric field in this region. Okay, the figure shows the electric field lines in the vicinity of 2 equal positive point charges. Again, close to either charge, the lines are nearly radial. The same number of lines emerges from each charge because the charges are equal in magnitude. At large distances from the charges, the field is approximately equal to that of a single point charge of magnitude 2q. But notice from these lines, you can see the repulsion of the 2 positive charges. Okay. This is a sketch of the electric field lines associated with the positive charge plus 2q and the negative charge minus q. In this case, the number of lines leaving charge plus 2q is twice the number of terminating on charge minus q. So that means only half of the lines that leave the positive charge end at the negative. I'm sorry. Let's close that. So that means only half of the lines that leave the positive charge end at the negative charge. The remaining half terminate on negative charges that we assume to be located at infinity. At great distances from the charges, which means great compared with the charge separation, the electric field lines are equivalent to those of a single charge plus q. And next, we're going to talk about conductors in electrostatic equilibrium.